You gotta turn it on. Hold on. How's that? Better? Okay. Hey everyone, thanks for coming. Really excited to see everybody on a Saturday. Yeah, so today I'm gonna tell you a little bit about doing end-to-end analytics on a GPU or a set of GPUs. So I don't know how much of you know about MapD, but MapD originally stood for Massively Parallel Database, coming out of my research at MIT. It's an open source project, or at least open core, so you can go on either GitHub or download our community edition that includes basically a full SQL accelerated GPU database that runs on anywhere from 1 to 16 GPUs per server. It's tremendously performant. We like to think it's basically the fastest OLAP engine out there, obviously meant for analytic workloads. And then on top of that, GPUs make sense for a lot of other things. So not just fast queries, but visualization. So it may not be surprising that you can leverage the GPUs for what they originally were designed for, which is rendering graphics, and we can do that right on top of the data. I'll talk about that. And also for machine learning. So MapD is not so much the machine learning platform in itself, but because we're part of this GPU ecosystem, I want to tell you a little bit about this project we've been working on with Anaconda, H2O, and NVIDIA called the GPU data frame, which is a way to seamlessly transfer results between different processes running on the GPU. So just quickly to set the stage, CPUs aren't getting as fast as they used to. So back in the day, people used to just crank up the clock speeds on these things, and they could easily get maybe 40 to 50% gains per year. At some point, engineers at Intel and AMD basically hit a wall where they realized that cranking up the clock speeds required exponential increases in energy consumption and heat generation. And so they started having to get more clever, going multi-core, adding bigger caches, adding better out-of-order execution pipelines. And essentially, the growth in CPU processing power slowed down a lot. And that happened right when the era of quote-unquote big data was taking off, right? So organizations were starting to get massive amounts of data, log data, sensor data coming off of cell phones, social media. And basically this gap, caused a lot of frustration for people. People had to start doing things like heavily downsampling, pre-aggregating, scaling out to massive clusters. I think until relatively recently, it was very cool to say, oh, I had a 1,000-node Hadoop cluster. People have realized that not only is that really expensive, but it's often a major headache to administer. So that sets the stage for the entrance of the GPU. So I don't know how much you know about GPUs, but GPUs obviously can do a lot more than just doing rendering Quake or Crysis to your screen. They've evolved into general purpose compute engines that leverage the same parallelism that allows them to render graphics performantly to basically do all kinds of operations. So it started with HPC. They're now generally programmable for the last 10 years. HPC, scientific simulations, evolved into machine learning and particularly deep learning. So deep nets and AI are all the rage, and most of them are running on GPUs, or at least being trained on GPUs. And then finally, we see the final frontier is general purpose analytics. You can leverage their massive parallelism and memory bandwidth to run things like SQL or just generic user-defined functions very, very fast. And so just to put it in a nutshell, the difference between a server running CPUs and a GPU accelerated server is that you have a ton of parallelism at your disposal. So a CPU server, you might have 10, 20. Some of Intel's chips, you might even have 30 or 40 cores on a dual socket system. An GPU server, which you can now spin up on any of the major cloud providers, as well as get on-prem from any major hardware vendor. You can have more than 40,000 cores now at your disposal. I don't want to say the CPU cores and GPU cores are the same, they're not, but this should give you an idea of what the parallelism you can get that's on tap with GPUs. So that's great to have this cutting edge hardware. One of the problems has been that there's been a dearth of software that's out there that can take advantage of the parallelism of these GPUs, right? So for select domains, yeah, there was specially written CUDA code or OpenCL code that could leverage these GPUs for things like protein folding simulation, Bitcoin mining. Well, now they've moved to ASICs for that, but some of the script mining, and deep learning. But if you wanted to do general purpose processing, like running a SQL engine, you were kind of out of luck. So that's where MapD comes in. Again, coming out of my research at the CCEL lab at MIT, we've been basically working on this for the last 4 or 5 years, building it into a very powerful engine that can do analytics SQL in real time. So the idea is taking multi-billion record data sets. I'll show an 11 billion record data set, and being able to slice and dice that instantly. Run queries, no indexing, pre-aggregation, just using the brute force scan power of these GPUs to basically run queries in milliseconds. And because one of the killer use cases of having this fast engine is being able to explore data, right? So, if you're running, if you have a classic data warehouse and the use case is to run a report, a static report for your CEO showing him the sales numbers from last quarter, you probably don't need a super fast database to do that, right? But with that speed, it really does enable a whole new form of interactive exploration of data. And that's why we built MapD Immerse. So MapD Immerse is a web-based visual analytics platform that leverages not only our fast SQL, so you can cross-filter and drill down on anything instantly, no pre-aggregations or indices required, but you can also use the GPUs for what they're originally designed for, which is to render data. So we can actually run the SQL query over billions of rows. The data stays on the GPU, and with zero copy, we can actually render that using our OpenGL rendering engine that's based on the Vega rendering specification. So more, before I dive into the more machine learning angle of the presentation, I'd just like to give a quick demo, since seeing is believing, I think. I'm going to start with this data set, relatively large. So this is ship AIS data. It's open data from the US Coast Guard. Basically every ship position from their GPS responder around US coastal waters from 2009 to almost the present here. So here you see different things. You can see that you can instantly basically cross-filter on anything. And you can see how fast that is. So again, we're just scanning this database. And every time I click on something, all the charts update. So it's a great way to kind of contextually explore the data. Similarly, I can brush over ship length, and we can see how fast that is. This is not a feature, but if you were to look at the SQL happening behind the scenes, this is what we're sending to the backend. And we're doing a brute force scan across 30 GPUs, 127 milliseconds, 172, 33, 56, 33, 26. So the speed is what enables this kind of extreme interactivity, if you will. And so it's fully interactive. And the last thing I'd like to point out is this map. There's no way you'd actually want to stream 11.6 billion records from your server to your client. You'd be sitting here all day. We actually leverage server-side rendering. So even though it feels like the data's in the front end, you can hover over anything, basically get some kind of contextual pop-up. You can drill down, do whatever you want. This is actually a server rendered image right on the GPUs. And so that allows us to scale past the normal visualization wall. So as I drill in here to San Francisco, we can actually say, I want to see all the, let's see, you might want to look at military ops. That's interesting. But you could look at, on your own time. You could look at, let's see, where's tanker? Yeah, you could look at the tanker, and right here, our office is pretty close to here. We can actually see these tankers basically circle in the bay as they're sometimes just waiting for the price of oil to go up. So it's profitable. Yes?
Have you tried, like off the cuff, how long these things would take, how long each query would take in a traditional database?
Yeah, that's a, yeah. I have a slide on this, and there's been some independent benchmarks, but I think they did, there's been some benchmarks, same, not this data set, but the 1.2 billion record taxi data set. That's pretty common. A lot of these kind of simple OLAP queries were taking 10 to 80 seconds. So a faster system like Redshift, I think they had a $50 an hour cluster of Redshift, was taking, I don't know, maybe 3 or 4 seconds. But that's per each query, right? So you still wouldn't have this kind of interactivity, and you certainly wouldn't have the rendering. Plus, that's 3 or 4 times what the cost of MapD would be, running on a single server. Since I'm at Twitter, I figured I had to quickly give a Twitter demo. Basically you can zoom in here. This is streaming up to the second. These are geocoded tweets. You can play with it. You can do any hashtag. I was trying to think of something that was like PC to search for, but I couldn't think of it. So I figured we could search for more. You can see the big spike about this guy down in Alabama, whatever he's doing, and what people are saying about him. So, and you can get very granular here. We can, again, basically zoom in and see what people are saying. Cool. That's for the next demo, actually. So I'll hold there. Let's see a time check. OK. So where does MapD fit into your overall ecosystem? So even though we are a SQL analytics engine, we don't generally go to market as a data warehouse replacement, right? So if you have a Vertica or Teradata, those systems have evolved. They're very mature. They don't have our speed, but we don't. We're basically at SQL 92. We're working on window functions, some of the more advanced SQL, but we're not going to have all the features. So what we normally do is kind of sit as a sidecar where we're like a hot cache on your stored record. And that could be pulling data out of a data lake or Hadoop system. That could be pulling data out of a traditional data warehouse like a Teradata via JDBC. You can pull in streaming data. You saw the Twitter was basically up to the second. You pull into MapD, it's going to be ultra fast because it's GPU accelerated. You can't hit third-party BI tools. We have a nice DB API compliant Python connector, which I'll talk a little bit more about in a minute. I'm going to actually, this is the focus of the rest of the presentation about doing kind of end-to-end machine learning, so I'll hold on that. And of course, you can leverage, a lot of our customers leverage MapD Immerse. Even though it's not as feature complete as a Tableau, it does allow for very agile exploration of very large data sets through the SQL and rendering capabilities. And one of the things we're going to do going forward is basically adding, using these GPUs to do kind of, you brush on some anomaly, and we can do a pairized logistic regression against all the other attributes in the data set, probably in a few seconds. And so basically it will augment the human and kind of give automated insights into what's going on in the data. So you asked a question of speed. This is this guy, Mark Litwinchik. He's done a number of benchmarks on different systems. Typically, we're orders of magnitude faster than the other systems, even though the other systems are running much larger hardware footprints, like a 50-node Presto cluster, 11-node Spark cluster, 6-node, $50 an hour Redshift cluster. And so this is actually a relatively small data set for us, right? This is 1.2 billion rows. We're running queries in 20 to 50 milliseconds, even on a single server with gamer GPUs. But imagine that scales, right? So as you get to bigger and bigger data set, the advantage that we have increases by leveraging these GPUs. All right, so getting to the meat of the talk, one of the exciting things we've been working on with, again, NVIDIA, Anaconda H2O, John Owen's lab out of UC Davis, the Gunrock folks, Graphistry, and a few other players, is this GPU data frame. And it's part of a larger initiative called GoAI, a GPU Open Analytics Initiative. And basically, it was designed to solve the problem that all these people were doing cool things on GPUs, right? We were doing more of the SQL and visualization piece. You had, obviously, all the deep learning frameworks like TensorFlow, Theano, Torch, doing neural nets. You had people like H2O actually pushing a lot of their non-deep learning ML to GPUs, like GLM and things like this. And you even had people like Continuum, now Anaconda, pushing Numba, where you could do general purpose compute on GPUs. The issue is that all these different platforms are relatively siloed, right? I'll just skip ahead to a slide here, in that if you had data on the GPU with MapD and we had a result set, you basically have to send it to the CPU, and then you have to send it, if you wanted to do some compute in Numba and Python on the GPU, you'd have to send it back to the GPU. And then if you wanted to do some kind of deep learning, you'd also have to send it back to CPU and back to GPU. And moreover, you probably would have to send it over the network, even if it was on a local host, the way most of these systems were set up. So that was a rather inefficient state of affairs, and basically any kind of real-time-ness that you could achieve out of all these platforms running on GPUs was largely destroyed by the overhead of marshaling data and sending it across the PCI bus from GPU to CPU and back. So just some motivating use cases that we found and that our customers use this for. So the first, and you don't even need necessarily this GDF for this, is we have a lot of data scientists using us for interactive feature engineering. The fact that it's so fast and you can slice and dice so quickly, people really like it to kind of discover anomalies in their data, visually discover correlations. We have a number of hedge funds using us to basically, when they get a new data set of, say, a new credit card data set or something that they want to try to mine to look for trading insights, they'll use both our query engine and Immerse to basically look for interesting features in the data. Also look for anomalies. The second one is interrogating black box AI models. So I think you hear a lot about this in the news where people say, hey, these especially deep learning models are very powerful, but we have no clue what they're doing under the hood. So we actually have Volkswagen using MapD to basically take their AI models and then put the results back into MapD and just do systematic comparison of the inputs and outputs, both algorithmically as well as visually, so that they can show their bosses and say, hey, there's no kind of correlation that's going to get us sued here between, say, a protected class and whether they're going to buy a car or something. And then finally, enriching data. So this is something I'm really excited about, is that a lot of this stuff, a lot of the heavy-duty deep learning is actually kind of hard to put in a database as a UDF. And so basically, we can have the ML, DL as a sidecar alongside MapD, and that we can actually say, hey, give me a sentiment on this text, or basically predict whether this person has the flu based on their tweets or something like that. And we can actually roll that prediction right back into our data tables, and then you can use that for further analysis. So when we all got together, the idea was, we're all running on the GPU. Let's have a zero copy framework such that we can pass data seamlessly between these different processes without the overhead of marshaling again, or going to the CPU. And because we didn't want to reinvent the wheel, we actually picked something that was already out there as a base, Apache Arrow. I'm not sure how many of you heard of this, but it's kind of an up and coming, let's see if I can put this right. Basically, it's an up and coming framework for both doing kind of IPC between different processes, as well as just a common in-memory columnar representation, such that these different processes can just seamlessly hand data off to each other, and they can all speak the same language and the same format of data. So we use that as our basis. Wes McKinney, at PMC on Arrow, and at 2 Sigma has been pretty heavily evolved. And this Apache, we basically added IPC support for it, so that on the GPU, if I want to give you my data, if MapD wants to give HO its data, it can basically write to this Arrow format and then just use CUDA's native IPC capabilities to hand that data off to the next process, and it's completely zero copy. So not only do you avoid the overhead of copying the CPU, but you actually avoid the overhead of copying on the GPU itself. And you can actually use this even inside different Docker instances. 3 minutes, okay, wow, okay. And it's great. So you can do, you can take data out of MapD, pass it through the data frame, pass it to something like Anaconda or these other processes. I'm gonna see if I can give a really quick rough demo. So even though you can do this programmatically through our Python connector, try to do it visually here. So this is very much a work in progress. And we were kind of working on it last night to get this going, so I can make no guarantees if this will work well, but hopefully it will. So this is flight delay data. I'm just going to give you a quick example. So imagine I wanted to look at JetBlue. Here I've average departure delay by origin state. I'm going to click on California, and now I want to see what the relation between, I already picked this, arrival delay and departure delay. And so here I would do train, and bam, it finished. I got an R-squared of 0.84, which is pretty good, but you might expect that there would be a good correlation. Maybe I want to say, I actually think airtime is a good feature as well. So I could use those same filters and click train, and well, it's about the same. So didn't have but obviously this is kind of the workflow that a data scientist might go through, that they could quickly apply filters and kind of clean their data. you could just clean the data through adding filters and then see how they can improve their models before they actually put their models into production. So interactive feature engineering. Great. So probably at 1 minute, I want to make sure I have time for questions. Just a quick thing is that Arrow, or the GDF, is not good just for outputting data. So we actually put it in our import path as well. So when you push data into MapD, if say you have a pandas data frame in Python, going over Thrift, which is our kind of default I/O mechanism, row-wise 42 seconds. We went to columnar 5 seconds. By using Arrow and doing IPC, we got it to 420 milliseconds, excuse me, for 3 million rows. But you can see the dramatic improvement of using IPC. So I won't touch on the use cases. We go across a number of verticals: telcos, financial services, what we do with the hedge funds. I'll just say that if you're excited about this and want to get involved, we are open source. Get us in GitHub. Download our community edition in Linux, CentOS, or Ubuntu. Works out of the box. Some people have gotten it working on a Mac, but it's not officially supported. You can spin us up on AWS Cloud. We have a community edition there. Obviously an enterprise edition. And yeah, we're a growing company. So if you're interested in working kind of cutting edge problems on GPUs, we'd love to chat with you. So thanks so much. Happy to take questions. Yeah. Oh.
How much data can you fit on a GPU?
It's a great question. So one of the things I didn't get to here is our memory caching technology. So usually we're running on more than one GPU, first off. So a lot of our customers run, like Verizon, I think has 4 nodes with 8 P40s each, which is, and they're moving probably to a terabyte of GPU RAM. We're a column store, so we actually compress the data heavily. And the nice thing is that we have this 3-tier caching mechanism where not everything has to go in the GPU. So everything by default, unless you define it as an in-memory table, will be stored on disk. As you query, we basically percolate the data up through CPU RAM to GPU RAM. It's kind of like a pyramid here. And so the hot data, the data that's actively queried, and we define that as things that you're doing active calculations on, will sit in GPU memory or will be streamed through GPU memory. Ideally, that can be cached across the multiple GPUs. And we find that, I think Verizon on 2 nodes had us running on a 20 billion record log data set. So pretty sizable with maybe 20 hot columns. And you can obviously scale out as you need to. But what isn't actively queried, or even just columns you're using for projection, can sit in CPU RAM. CPU RAM is typically much bigger, so it gives us a bigger footprint. And we can actually execute in CPU if necessary. If it doesn't all fit on GPU, we'll use our LLVM compilation engine to actually run on CPU. We can target CPUs. We're quite fast there, obviously not as fast as GPUs. So it's a pretty flexible system. All right. Happy to chat with anyone after. Thank you.